Well, hello. Problem number 69 from chapter 10 is a good problem because it ties together or it brings together problem solving techniques from the current chapter, chapter 10, which has to do with work and energy conservation, and also the dynamics of circular motion, which you learned back in chapter 8. We need both techniques in order to solve this problem. I tried to reproduce this figure faithfully from your book, but you can find it on page 260. This was not assigned. We've got a ball on a piece of string. Think of it as a pendulum. And this ball has been pulled out until the string makes an angle theta with the vertical. Then the ball is released. It's allowed to fall under the influence of gravity. But then it hits this, as it's falling, the string right about here, the string's going to hit this peg. This is a peg that goes into the board. And the string starts to wrap around, twirl around. And you can imagine that if you threw this ball quickly downwards, it might wrap a whole bunch of times around the peg before it stopped. On the other hand, if you only pulled it out a little ways, like let's say out to just 10 degrees, and then dropped it, this ball might just kind of rise a little bit and then fall back down. Or maybe you pulled it out far enough that the ball went all the way up here, and then at the top it started to fall back down. What the problem is asking is, how far out do you have to pull this? To what angle theta, so that this ball will not just make it around, but so that it'll make a complete circle around the peg, so that the tension doesn't go slack, as they put it. In other words, the tension needs to be greater than or equal to 0. If the ball is going too slow as it passes through the vertical, it's going to go around like this, at least on the first pass. If it's going too slow right here, then the tension in the string would drop to 0. And that's another way of saying that the string goes slack. So we've seen problems like this before. It's kind of like the news anchor that was twirling the bucket of water around. That video should be on Canvas. You have to twirl the bucket with a sufficient speed so that the water doesn't fall out. Same thing here. Okay. Well, if you're wondering how do you go about starting, remember it's chapter 10. Take a hint from which chapter you're in. This is probably an energy conservation problem. So you should ask yourself what types of energy we're looking at here. I don't see any springs, so there's no elastic potential energy, but stuff is moving, so we have to deal with kinetic energy, and of course there's gravity. So it's just going to be the combination of gravitational potential energy and kinetic energy. Before you can apply this formula for potential energy, you have to choose your origin. Remember, this coordinate y gives you the coordinate with respect to an origin. So first you have to pick your origin, and that's totally up to you. It's not going to affect the physical conclusion that you draw from the math, but it will affect your equations a little bit. So make a convenient choice. To me, the obvious choice, or one obvious choice, would just be at the bottom of the swing. This is the lowest point that the ball achieves. I'll call this y equals 0. And this isn't necessary, but let me pick some subscripts for it. Times. T0 is when the ball is released, and T1 is when the ball reaches the top. The ball is at the top of its little twirl around the peg. So now I have some convenient subscripts to work with, and I don't see any, well, let me back up. The only force I see acting here would be, the only two forces are gravity and tension. I'm talking about the forces on the ball. The system here is the ball. You might say that the system includes the rope, but remember, in most of these problems, we pretend that the strings and ropes are massless, so they don't have any kinetic or potential energy. We're talking about the energy of the ball. Now, the only thing touching the ball is the rope, so the rope might be doing work on the ball. Gravity is, of course, also doing work. On the way down, gravity is doing positive work. On the way up, gravity is doing negative work. But see how tension pulls this way? Do we need to worry about the work done by tension? Notice that the instantaneous velocity of the ball is always tangent to the trajectory. Here's the tangent direction. You see that the angle between those two is 90? It's a lot like the normal force when a ball is rolling along some sort of ramp. The work done by the normal force is 0 because the normal force is always perpendicular to the motion of the object, the ball that's rolling, for instance. So we can say that the work done by the tension is 0 since tension dotted with infinitesimal displacement is always 0. If you go look at the work integral of F dot dr, the integrand is 0. Now, do we need to calculate the work done by gravity? We don't. That was what was done in chapter 9. But we've moved on to a more convenient viewpoint. We're not talking about work done by gravity anymore. We're talking about gravitational potential energy, which is related to work. But that's behind the scenes. We've already taken care of that. So in this chapter, we assume that the gravity field is uniform over any vertical displacement, and then we just use this simple formula. Okay, so the most general equation you could start with for a lot of these problems, the equation introduced by your book, would be this one. Work done by external forces has to equal the change in total energy of the system. That's it. This is a statement of conservation of energy. If there's no so-called external work being done on your system, then the change in total energy should be 0. In other words, the total energy should not be changing. It is conserved. Well, in this case, that's true. I don't see any so-called external forces. So that's gone, and we can say that 0. Remember, this has 2 contributions. The increase in thermal energy, which might be present, and then the change in so-called mechanical energy. Now, off to the side, I will remind you that thermal energy comes from the work done by dissipative forces. In reality, air drag would be doing dissipative work on this ball. As the ball falls through its swing, there's going to be an air drag force opposite the motion of the ball, and that will tend to sap mechanical energy from the system. Of course, if you just let this swing back and forth forever, well, it won't go forever. It'll settle down and come to a stop, because the mechanical energy of the system in real life does get dissipated by friction and air drag. But we're pretending that those are negligible in this problem, so there's none of that either. And then I'm going to break this up into its 2 components. For this problem, you've got the change in gravitational energy and the change in kinetic energy. So you could have started from here, but honestly, an even easier place to start would be to recognize, well, this is final minus initial, and my initial and final times are T0 and T1, so I can use the same subscripts to label those quantities. Just move all the initial stuff on, I'll put it on the right side and the final stuff on the left side, and I get this expression. UG at time 1 plus kinetic energy at time 1 must equal the gravitational energy at time 0 plus the kinetic energy at time 0. So it is true that the kinetic energy up here may be greater than what we started out with, and maybe the gravitational energy is less than what we started out with. It all depends on what we calculate, but the sum will not change. There's an exchange between kinetic and potential. The gravity field is transforming energy from potential into kinetic and back again. The force is what does the transformation. And we're just recognizing that there's this scalar quantity called total mechanical energy, which should not change during that process. Okay, now because of my choice of coordinate system, I think we're ready to evaluate the various quantities here. Now we're told that the ball is released from rest. So the kinetic energy at time 0 is 0. That makes that easier. And now we have to use a little bit of geometry. Okay, first of all, let's note that the y coordinate at time 1. That's when the ball is supposed to be right here. We're looking at when the ball reaches the vertical and asking if the tension is greater than 0. Well, let's see here. If the string has a length of L and this peg is 1/3 L above the bottom of the trajectory, then wouldn't an amount of string equal to 1/3 of L have to have wrapped around the peg? Hopefully you see that this also has to be 1/3 L, because the bottom of the string would have been here anyway. So when the ball gets up here, we've got 1/3 L plus another 1/3 L. The ball will be at a height 2/3 L above its lowest point at time 1, 2/3 L. So now we'll be able to plug that y coordinate into our formula for potential energy so that we can evaluate the potential energy at that time. Now the height at time 0 is a little more complicated. Rather than draw another diagram, I think I'll just use this one. When in doubt, draw a right triangle. whatever this angle is, we need to specify this initial height in terms of theta. Now, don't be misled by my drawing here. It's just a coincidence that the ball appears to be at the same height as the peg above the bottom point. I just happen to draw it that way. In fact, it's a little higher. So forget about the peg. We need this distance right here. Well, what's this total distance? Remember, this would be the bottommost part of the swing, or it is the bottommost part of the swing before the string starts to wrap around the peg. So that means that this total length would have to be L. It's just the same as the length of the string. So let's take L and subtract the adjacent side in this triangle. I'm saying adjacent because I mean adjacent to theta. If we could take this total length here and subtract the adjacent side, we would have the distance we want. Again, don't be, you know what? Let me just sketch this somewhere else real quick so you're not misled by that coincidence. Okay, so I'm not even going to draw the peg. Here's theta. And we need this. I'm going to call this y0. That's the y coordinate at time 0, because remember, this is the origin, for the y-axis at least. Okay, so if I could take this, which is L, and subtract this, I would have y0. Well, look at the right triangle here. This hypotenuse is the length of the string. That doesn't change. So if I take L and multiply by cos theta, I get this adjacent side. And we agreed that the whole thing is just L, so this must be L minus L cos theta. Does everybody see that? Take the total length of the string and subtract the adjacent side. Now, I can write this a little more simply by factoring out L. You're going to see this again. This shows up in a few problems, so it's worth remembering, not necessarily memorizing. But over here, I'll write the y coordinate at time 0. That's the time at which the ball is dropped, is L times 1 minus cos theta, where theta is that initial angle. Now, I could call it theta naught to be consistent with the time, but since I'm only labeling one angle, theta is the particular angle from which the ball is dropped. Okay, so let's plug stuff in now. The potential energy at time 1, well, that's just mg times y1, and we know that's 2/3 L. So this is mgy evaluated at this particular y coordinate, plus the kinetic energy at time 1. I don't actually know the speed yet. And UG initial, well, that would be mg times y initial. I'm substituting the expression we found for y initial. And the next thing, you may be wondering, where do we go from here? Remember, we're trying to find the required theta. Find theta so that the string doesn't go slack at the top. The ball needs to be going fast enough that there's still, barely some tension in that string. So really, the value that theta must take is, how do I put this? The minimum value of theta, because we know we could drop it from higher and it would whip around faster. The minimum value of theta is determined by how fast it needs to be going at the top. So why don't we first put v squared all on one side and put everything else on the other side. And while we're at it, we can divide out the m, see that? And I would like to get rid of this, this 2 as well. So I'm going to multiply the whole equation by 2 over m, and then I've got 4/3 GL plus V1 squared equals 2GL times 1 minus cos theta. And there's that 2GL, 2G times height that we keep seeing. Remember root 2GH? That's kind of what we're looking at here. So like I said, I'm going to put the V squared on one side and everything else on another side. I think what I'll do is put this on the left. You'll see why. So 2GL, actually negative 2GL times 1 minus cos theta plus 4/3 GL. Hang on a second. Made an algebra error. I had it right the first time. 2GL times 1 minus cos theta minus 4/3 GL. That's got to equal V1 squared. Okay. Check my work there. That should be good. So now we need to figure out what the restriction is on V1. What's the minimum speed that the ball has to have at the top so that it makes it around? Once we know that minimum speed, we can plug it in here and solve for the required theta. So I'm going to put this off to the side, or actually I have space now. Let's look at the dynamics now, the circular dynamics. So maybe you solve this problem in the opposite order if you took a look at this problem. Maybe you want to do the dynamics first. Okay, so here's the peg. And when the ball is at the top there, we need the tension to not be zero, or let's put it this way, not negative. The ball has to just barely make it around without the string going slack. So I see two forces on the ball here. There's the tension downwards, there's gravity downwards, and I will apply the dynamics of circular motion. Note that downwards is towards the center of the circle. And the peg actually is the center of that circle, right? Because the string is wrapping around the peg. So I'll say some of the forces along the r-axis is mass times acceleration along the r-axis. We've got three different formulas for this acceleration, but we're interested in v, so I'm going to use the formula that involves v. T plus mg, they both point towards the center, they both get a plus sign, mv squared over r. Okay. Now the condition for the rope not going slack is that the tension has to be greater than or equal to 0. So tension, if I solve for T, I'd have a negative mg over here. How about I factor out the m? It would be m times v1 squared over r minus g. That's got to be greater than or equal to 0. This is the tension in terms of these other quantities. Well, see how we could just divide m from both sides of the equation. What we're really saying is that v1 squared over r minus g has to be greater than or equal to 0. Or in other words, v1 squared over r has to be greater than or equal to g. And that's a very nice result. We've seen this before. V squared over r, that is the centripetal acceleration. So the centripetal acceleration really needs to be greater than or equal to the free fall acceleration. Now, the ball could be whipping around here at like 5 Gs, 10 Gs, and there would be a lot of tension in the ball. But if you slow the ball down, 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 and you get its centripetal acceleration down to just 9.8, that's when the rope just starts to go slack, because at that point, no tension is needed. Gravity alone is sufficient to provide the centripetal acceleration. It's just one idea there, but it's one of the most profound and cool ideas from the whole semester. If you understand that, you understand something that nobody understood in Galileo's time, which is pretty cool. I can confidently say that because Galileo died the year that Newton was born, I believe. And we know that Newton didn't figure this stuff out as a newborn, did he? So it's a subtle point, but if something is moving in a circle so that at the top of the circle, the only force is gravity, well, then we know the centripetal acceleration has to equal the gravitational acceleration. Okay, so we've got our restriction on V. In other words, V1 squared must be greater than or equal to RG. Well, what is the radius of this circular path? Might be easier to answer that by looking at the original. Yeah, if we continue the circle, remember, it doesn't actually have to make a full circle around the peg. It might, but we don't care about that. We're just looking at what happens up here. The radius here is this 1/3 L. That's the radius of the circle, not the full L. So I can set this equal to L over 3G. Okay, so the upshot here for this part of the problem is V1 squared has to be greater than or equal to L over 3G. Okay, it makes sense. The longer the string is, the faster it needs to be going at the top so that the string doesn't go slack. Now let's go back to this equation. V1 squared from conservation of energy is less than or equal to or greater than or equal to, is equal to this, because all the kinetic energy at the top is coming from that initial potential energy. So if this has to be greater than or equal to 1/3 Lg, then this must also be greater than or equal to 1/3 Lg. So I'll continue the algebra here and say, I think I'll distribute here 2GL
minus 2GL cos theta minus 4/3 GL. Well, that's got to be greater than or equal to L over 3 G. We just determined that by looking at the dynamics of circular motion. So the dynamics, that's F equals ma, you're talking about vectors. Here we're talking about scalars. This is the energy statement. Okay, how do we proceed from here? Ultimately, we're trying to solve for theta. So what I'm going to do is move this theta term to the other side, and I will also divide by L. I won't skip any steps here. Can I divide by G? Yeah, check that out. We can get rid of L and G. GL gone, GL gone, GL gone, GL gone. That's nice. So 2 minus 4/3 must be greater than or equal to, well, what we've really got here is 1/3, right? All I did was divide out LG, but there's still a factor of 1/3. So 1/3 plus 2 cos theta. Don't forget about the factor of 2 out front. Okay, I'm going to flip this because it's a little easier to look at that way. 2 cos theta must be, now, okay, for a minute I was thinking, wait a minute, it shouldn't say greater than or equal to because we're looking for the minimum possible angle of theta, but we'll get to that in a second. So 2 cos theta plus 1/3 is less than or equal to, and let's see if I can combine these right now. If I want to subtract these, I need a common denominator. So how many thirds is 2? Just multiply top and bottom by 3. So 6/3 would be the same as 2. 6/3 minus 4/3 is 2/3. All right. And then let's subtract 1/3 from both sides. 2/3 minus 1/3 is 1/3. Lastly, divide by 2. And wasn't this obvious from the start? Of course, the angle must be greater than the arc cosine of 1/6. I was able to tell that immediately, but you know, I didn't want to spoil the problem for you, so I showed you the slow way of doing it. Of course, that's not obvious. Now, why does it say less than? Because we know that the angle must be greater than or equal to some minimum angle in order for the ball to make it, excuse me, in order for the ball to make it around without the rope going slack. So don't forget, when you look at the cosine function, it actually drops between 0 and 90. So we're saying that the cosine needs to be less than or equal to some value. Look at the value of cosine. It needs to be less than. Let's say this is the max possible value of cosine of theta. Well, that means we can't have angles of theta in here because then the cosine function will be greater than the max possible value. So we need some angle greater than this angle. This is the angle that we're interested in. So in other words, the cosine of theta min, is equal to 1/6. Go ahead and replace that inequality by an equality to find the cutoff point. I say theta min because an angle greater than theta min would be okay, and the rope still wouldn't go slack. Okay, so theta min equals, the suspense is killing me. What is the arc cosine of 1/6? 1 divided by 6 equals, take the arc cosine, 80.4. Woo, that's way up there. The string would need to be even higher, approaching 90 degrees. If you drop it from an angle of 80.4, it's going to make it all the way around without the string going slack. In other words, the ball's not going to dip at the top. It'll actually clear the circle. Okay, not a trivial problem. It had multiple steps. You had to apply 2 different physical principles: the dynamics of circular motion, that's Newton's second law for circular motion, and also this principle of conservation of energy. I say conservation because there's no work done by so-called external forces.